So you probably already know that when you jump up, you're bound to come back down, and that's because of gravity, or the force that the Earth is exerting on you. And we already know from Newton's third law that the force that the Earth exerts on you is going to be of the same magnitude but the opposite direction of the force that you exert on the Earth. And that's a little weird to think about because we don't really see the Earth move with respect to us, but we are in fact exerting the same amount of force onto the Earth that Earth exerts on us. We just don't really see it since the Earth's mass is so huge. And so Newton decided to analyze gravity and the forces that objects exert on each other in relation to the products of their masses. So m1, which is the mass of the first item, and m2, which is the mass of the second item, versus the force. And he also looked at force versus the distance between the two items. And so the graphs that he observed look kind of like this. And so for the force versus product of the masses graph, he noticed that as the product of the masses increases, the force also increases, and it's a linear relationship. So we can say that there's a direct proportionality, so F is directly proportional to the product of mass 1 and mass 2. And that makes sense because if we draw free body diagrams for, let's say, a bee and a piano, then we'd know that this vector, mg, which is mass times the acceleration caused due to gravity, for the bee would be much smaller than the vector for the piano, because the Earth has to pull much harder on the piano since its mass is greater than the bee. And so in this case, with mass 1 being the mass of the bee and mass 2 being the mass of the Earth, let's say that it's somewhere over here, so it's not that big of a quantity. And then the second case, where mass 1 is the mass of the piano and mass 2 is the mass of the Earth, we could say it's like somewhere over here because the piano has a much greater mass, and so the force is going to be much greater than the force exerted on the bee by the Earth and vice versa. Now for the force versus distance graph, we can see that it's not linear, so it has a kind of curve to it, and so we can call this an exponential function because it looks like the function 1 over x squared. So as distance increases, the force rapidly decreases. So F is directly proportional to the inverse of distance squared. And the fact that it's proportional to the distance squared tells us that if we have two objects and they're very close to each other, then the force between them is going to be much greater than if they were, say, this far apart. And if you kept separating them more and more, then eventually they'd be so far apart that the force between them would be almost zero. So here, as you can see, if you move all the way to the right, then the force is going to be approaching zero. And now we can combine all of these ideas into just one expression. The gravitational force between two objects is equal to a constant, which is called g, and I'll talk about that more a little later, times the mass of the first object times the mass of the second object. So remember, this is coming from our proportionality that said force is directly proportional to the product of the two masses over the distance squared. And this part, of course, is from force is directly proportional to the inverse of the distance squared. And so this constant is just a number, and it's a very small number. It's equal to 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. And typically you won't have to memorize this because they'll just give it to you on an equation sheet or something, but it's just a number that's going to be used in calculations involving this universal law of gravitation.